Welcome to your AP Statistics Chapter 16 lesson on random variables. Okay, a random variable assumes a value based on the outcome of a random event. We use a capital letter like capital X whenever we want to denote a random variable, and then a particular value of the random variable is represented by a lowercase of the same letter. There are two types of random variables. One is discrete, and those can take on one of a countable number of distinct outcomes. So, for example, it could be the number of cars in a parking lot. A continuous random variable can take any numeric value within a range of values. So, for example, the height of men, the weight of chinchillas, anything that it can be any number within that range, that's going to be continuous. Okay, a probability model for a random variable consists of the collection of possible values of a random variable and the probabilities that those values occur. So here's an example of a probability model or distribution of a discrete random variable. Anytime you can put all of the values of x or all the values of your random variable in a table, then you're working with a discrete random variable. Okay, so we've got all the values, and then we have probabilities listed for each value. Of particular interest is the value we expect a random variable to take on, and that's noted mu for population mean or e of x for expected value. And so for a discrete random variable, you're going to be able to calculate that mean or expected value by taking each of the possible values of the random variable, multiplying it by the corresponding probability, and then adding up all of those products. One thing to note is that whenever you're working with random variables, when you consider the probabilities, they have to add up to 1. And that's because 100% of every outcome should be, or 100% of the possible outcomes should be represented in a probability model. Okay, we have the center. Now we want to be able to measure the spread, and we do that by calculating the variance and the standard deviation. So you have to calculate the expected value or the mean first, because again, to find the variance, we are going to look at the difference between each value and the expected value, the mean. We're going to square that, and then we're going to multiply by the probability of x, and then we'll go to the next value for x and do the same process and so on. And that sum is going to give us the variance. So to find the standard deviation, we will then take the square root of the variance. Okay, if you add or subtract a constant from all the data, all the possible outcomes, what's going to happen is your expected value is going to have that same constant added or subtracted from it. The thing is, that doesn't increase variability at all. So your the variance is going to equal what it was before we added anything to it. Okay, so an example of this would be if a company decided to give everybody in the company a $5,000 increase in salary. It's going to shift the mean salary up $5,000, but it won't do anything to the variance or standard deviation. In general, if we multiply each value by a constant, then you're going to be able to multiply the mean value by that constant, and you'll multiply the variance by the constant squared, so that when you take the square root, standard deviation is equal to the constant times the original standard deviation. So consider if the company decides, instead of giving everybody $5,000 across the board, they're going to increase everybody's salary by 10%. Sometimes, instead of adding or subtracting a constant, we want to add or subtract a random variable from another random variable. So the mean of this sum, or the difference of two random variables, is very intuitive. If you're adding them together, then it's equal to the mean of the individual random variables added together. If you're subtracting y from x, then it's going to be the mean of x minus the mean of y. That's very intuitive. Now, variance, there's a little more to think about. For one thing, we don't use standard deviations in this formula. You'll hear me say all the time, variances add, standard deviations do not. So we're going to be working with the variance, and then once we're done with our formula, we'll take the square root of whatever we get, and that'll be our standard deviation. The really interesting thing is whether you add two random variables or you subtract two random variables, the variance increases. We get more variability in the possible outcomes. And so we always add the variance of x and the variance of y. Okay? And then if you want standard deviation, you just take the square root of that sum. Okay, so remember, if a random variable can take on any value in a range of values, you're working with a continuous random variable. So since it's continuous, the probability of any single value doesn't make sense. What we will be doing is looking at ranges of values and finding probabilities based on that. They do have means and variances. We're not going to worry about how to calculate those in this course, but we will still work with models for continuous random variables when we're given the parameters. So, for instance, means are typically summary statistics of continuous variables. So, when you're looking at quantitative data. The good news is nearly everything we've said about how discrete random variables behave is true of continuous random variables as well. So when two independent continuous random variables have normal models, so does their sum or difference. So this means we are going to be working with normal distributions again. So you might want to go back and look at Chapter 6 and refresh what you know about normal distributions. This fact will let us apply our knowledge, like I said, from Chapter 6 whenever we're working with the sum or difference of two random variables that are normal. Okay, so for example, we're going to look at 2A from page 383. We are going to find the mean of the probability distribution. And so that's the same thing as the expected value. And so you're going to take each possible outcome, multiply them by their corresponding probability, and add that together. So 0 has a probability of 0.2, so we multiply those together, and then we add. 1 has a probability of 0.4, so we multiply those together, and then we add. 2 has the probability of 0.4, so we add that too, and we get 1.2. All right, so exercise 10A, we're going to find the standard deviation. Remember, it's the square root of the variance. We have already found the mean, the expected value for this formula. So we're going to take that expected value and subtract it from each observation. So 0 minus 1.2 squared times 0.2 plus 1 minus 1.2 squared times 0.4 plus 2 minus 1.2 squared times 0.4, and we get 0.56. Now, sometimes students want to know, well, why don't we divide by n? Well, the reason we don't do that is because not all of the outcomes are equally likely. So we weight each part of the sum by the likelihood that that particular outcome occurs. So we weight this first term by 0.2 because that's the likelihood of 0 occurring. We weight the next two terms each by 0.4 because that is the likelihood that either a 1 or a 2 is the outcome. So we get that our variance is 0.56. We take the square root of that and we get 0.748, and that is our standard deviation. All right, look at exercise 30 on page 385. Our random variable in this case is the number of good seeds in a packet. The expected value for x is 18 and the standard deviation is 1.2. And so the variance of x is going to be 1.2 squared, which is 1.44. All right. We want to know the expected value of the number of bad seeds in 5 packets. So we are going to have 5 different draws of that random variable because each packet, it has a different number of good seeds in it, or the number of bad seeds in it. And so what we're going to do is we're going to do the total number of seeds minus the expected number of good seeds in 5 packets. So we're going to do 5 times 20 to get a total of 100 seeds. And then we're going to find the expected value of x1 plus x2 plus x3 plus x5. So that's going to be the expected amount from packet 1 plus the expected amount from packet 2, expected from packet 3, expected from packet 4, and expected from packet 5. So that's going to be 100 minus the sum of 18 plus 18 plus 18 plus 18 plus 18, or 5 times 18. So it's 100 minus 90, and we get 10. We want to find the variance of the same thing, and so we're going to do the variance of x1 plus the variance of x2 plus the variance of x3 plus the variance of x4 plus the variance of x5. And so that's going to give me 1.44 plus 1.44 plus 1.44 plus 1.44 plus 1.44. So 5 times 1.44, and we get 7.2. Now, notice that this is different from just saying, okay, we have from the same manufacturer, we have a giant packet of seeds that is 5 times as large as the original packets of seeds. That would be a different thing. We have 5 different selections that will have values from the random variable. So this is different. You're not going to use the formulas for multiplying by a constant here. You're going to think through, okay, I'm adding this 5 times. All right, so your standard deviation of x is the square root of the variance, and so it comes out to be 2.683. For part C, the assumption we've made is that packets of seeds are independent of each other. If all the seeds are the same type from the same lot, then this may not be a valid assumption. So that's an assumption we're making, but we need to be aware that it may or may not be a valid assumption. All right. So go ahead and look at exercise 38 from page 385. All right, the expected value of D is 100 with a standard deviation of 30. It's good to go ahead and consider what the variance would be, so it's 900. The expected value of C is 120, standard deviation is 35, so the variance is 1,225. All right, so what's the expected value of D minus C? Well, that's the expected value of D minus 6 of expected value of C. So 100 minus 120 is negative 20, so negative $20. To find the standard deviation of D minus C, that's going to equal the square root of the variance of D minus C. Variances always add. You're always going to end up with more variability whenever you combine 2 random variables. And so it's going to be the variance of D plus the variance of C. And so 900 plus 1,225 gives us 2,125. Now we can find the standard deviation by taking the square root of the variance. And so it comes out to be $46.10. Okay, so we're going to let D minus C, that combined that combination of the 2 random variables, equal x. Since both D and C had a normal distribution, X does too. So X is normal with a mean of -20. We've just figured that out, and a standard deviation of 46.10. So we want to know the probability that X is greater than 0. So just for practice finding Z's, let's find Z, the standardized score for X. And so that's going to be X minus mu over sigma. So 0 minus -20 over 46.10. And so that's 0.434. And we're going to do the probability that Z is greater than 0.434, and we get 0.332. So how did we do that? We did normal CDF. Okay, so we did normal CDF, and we did the area to the right of 0.434, which is 0.332. If we find the z-score, we don't have to change the mean and the standard deviation from 0 and 1. Alternatively, you could have put in 0 and changed the mean to -20 and the standard deviation to 46.1, and you would get the same probability. Okay, guys, go ahead and try your problems to try on your own. If you have questions, please email me or stop by my class. Um, I look forward to seeing y'all and working with these random variables.